keeps modern railways running safely and smoothly. Let's discover the powerful technology behind rail replacement and precision rail welding. The process begins at the rail joint, where a bright silver section marks the exact location to be welded. This area has been previously ground by a worker to remove surface irregularities, oxidation, and contaminants. Grinding ensures that the rail ends are clean and properly aligned, which is essential for achieving a strong and uniform weld. Once preparation is complete, the flash butt welding machine is positioned over the rail joint. The welding fixture clamps firmly onto both rail ends, holding them securely in place. Hydraulic rams mounted on the fixture are aligned with the rails and prepared to control their movement during the heating and welding stages. Electric current is then applied across the small gap between the rail ends. Pulsed alternating current, typically between 600 and 700 amps, flows through the contact surfaces. This electrical resistance generates intense heat at the rail ends. As the current continues, the steel at the ends of the rails rapidly heats up and begins to glow. When the temperature reaches approximately 1500 to 1700 degrees Fahrenheit, the steel becomes plastic and suitable for forging. At this moment, the hydraulic rams activate and push the two heated rail ends toward each other. The force applied by the rams causes the softened metal to fuse together, forming a single continuous rail. Excess molten material is squeezed outward from the joint, indicating that proper fusion has occurred. The newly formed weld remains visibly glowing, showing that the steel is still extremely hot. This glowing section confirms that the rails have been successfully fused at the joint. The welded area is allowed to cool gradually, stabilizing the structure of the steel and locking the rails into one solid piece. After the welding operation is complete and the joint has cooled sufficiently, the flash butt welding machine is released from the rail. The clamps are removed and the hydraulic rams retract. The welder is then packed up and moved away from the track, leaving behind a continuous welded rail section ready for further finishing or inspection. The rail welding process begins with careful preparation of the existing track. A technician first inspects the rail line to identify sections that are worn, cracked, or deformed. Once the defective areas are located, the worker uses a handheld cutting and grinding machine to mark the exact points where the rail must be cut. This step is essential because only damaged portions should be removed in order to maintain the correct geometry and length of the track. After marking, the operator cuts the rail precisely at the selected positions. The cutting tool creates clean and straight surfaces on both rail ends. These flat and accurate faces are necessary so that the two rail segments can later be joined together without gaps or misalignment. Grinding is also performed to smooth the edges and remove any irregularities that could affect the quality of the weld. Proper preparation at this stage ensures that the rails will fit together perfectly during the welding operation. Once the rail ends are fully prepared, the Schlatter AMS-60 mobile flash butt welding machine is brought into position. The machine is placed directly over the gap between the two rail sections. Powerful hydraulic clamps secure each rail firmly in place. The AMS-60 then performs precise horizontal and vertical alignment to guarantee that both ends are positioned correctly relative to each other. This alignment process is critical for producing a straight and durable rail joint. The actual welding operation begins when the machine presses the two rail ends together under high force. At the same time, a strong electric current is passed through the contact surfaces. This creates intense heat, causing the steel at the rail tips to soften and melt. As the pressure continues, the molten metal is forged together, forming a solid and continuous joint. Throughout the entire procedure, the AMS-60 carefully controls pressure, temperature, and alignment to achieve a high-quality result. After the flash butt welding cycle is completed, excess material created during the process is trimmed away. The weld area is then ground and finished to match the original rail profile. This ensures that trains can pass smoothly over the joint without vibration or impact. The completed weld is visually inspected to confirm that it meets technical standards. The mobility of the AMS-60 allows the entire operation to be carried out directly on the track, making it suitable for both maintenance and new construction projects. By following this structured sequence, cutting, aligning, welding, and finishing the video demonstrates how damaged rail sections are efficiently replaced and joined into a continuous, reliable railway line using modern welding technology. A ballast cleaning machine is a specialized, self-propelled railway maintenance machine designed to excavate, clean, and restore track ballast without dismantling the rails or sleepers. During operation, a powerful continuous excavation chain moves beneath the sleepers as an undercutter, lifting fouled and compacted ballast from the track bed. The material is transferred to onboard screening and sifting units where soil, dust, and other impurities are separated. Cleaned aggregate is then returned to the track through conveyor systems, while waste is discharged away from the line. This process improves drainage, renews ballast quality, and restores proper track geometry. Modern high-capacity machines, such as the HOBCM RM900, can achieve impressive production rates of 450 to 500 meters per hour, ensuring efficient, mechanized railway maintenance operations. The long rail replacement work carried out on the upline seaside track between Yui and Okitsu on the historic Tokaido Main Line represents a highly coordinated maintenance project performed within a strictly limited night possession. According to the available information, the on-site footage was filmed in the early hours of February 14, 2014, documenting almost every significant activity occurring between the last passenger train and the first train of the following day. Consequently, the project provides a valuable insight into Japan's highly disciplined approach to railway infrastructure maintenance, especially on one of the country's most important rail corridors. To begin with, the section selected for renewal lies along the coastline, making it particularly exposed to sea winds, salt corrosion, and dynamic loading from heavy rail traffic. Therefore, the replacement of the seaside long rail on the up track was essential to secure long-term stability and riding performance. The long rails, measuring approximately 400 meters each, are characteristic of modern Japanese railway engineering, where the use of continuous welded rail, CWR, greatly improves track quality, reduces joint noise, and minimizes maintenance requirements. Because of the weight and length of the rail, the delivery and placement required careful planning long before the actual exchange took place. In fact, the new rail had already been transported to the site on September 15, 2013, by a special rail transport consist known as Ronkiya, long rail carrier. After delivery, the rails were temporarily stored along the alignment until suitable working conditions and scheduling allowed replacement. This method, common in Japanese railway maintenance, ensures that rail supply and construction machinery are ready and waiting, so that the actual intervention can be executed rapidly during a very narrow possession period. On the evening of February 14, 2014, operations commenced immediately after the final passenger train passed, which according to the information occurred at 23:59. Shortly after midnight, workers entered the track and machinery moved into position. Because the possession window was extremely small, all activities had to be prepared in advance, including safety planning, work sequencing, and the deployment of specialized track machines. At this stage, the existing rail was unclamped and prepared for removal. Rail fastening systems were released in a specific order to avoid destabilizing the track structure prematurely. Subsequently, the old long rail was lifted and slid laterally using hydraulic equipment and purpose-built rollers, enabling controlled movement along the track without damaging sleepers or ballast. Simultaneously, the replacement rail was pulled into place from the storage area using synchronized winching devices. This pulling operation requires precise alignment to prevent twisting or bending of the new rail, and workers continuously monitored clearances, geometry, and railhead position. The entire exchange of a 400-meter rail segment was accomplished with remarkable efficiency. Once in position, the new rail was fastened using insulated clips, plates, and anchors. Crew members inspected each fastening one by one, ensuring torque accuracy and confirming proper seating. The rail joints at the ends of the segment, whether welded or temporarily jointed, were carefully secured to guarantee continuity for the first train scheduled after reopening. In addition, attention was paid to lateral and longitudinal expansion allowances, which are crucial in continuous welded rail installations. By approximately 1:30, the documentation states that the main work had already been completed. This means that all fastening operations, alignment checks, and safety inspections were finalized in less than 2 hours of track possession, an achievement that demonstrates the efficiency of Japanese nighttime maintenance strategies. After that, crews withdrew equipment from the track, restored safety clearance, and prepared for train operations. Right before 2 o'clock, the first train of the early morning, specifically a freight service, successfully passed over the renewed section without incident. The safe passage of this train served as immediate proof of successful installation and stability. Only after the confirmation of proper train running could the section be considered officially reopened. As shown in the video, nearly all critical steps occurring between the final train and the first incoming movement were recorded, providing rare and valuable documentation of this sophisticated rail exchange procedure. In summary, the long rail replacement on the Tokaido main line between Yui and Okitsu illustrates a combination of meticulous planning, advanced technology, and disciplined execution. By transporting materials months in advance, organizing night work precisely after the last train, and restoring operations before the first train of the next day, Japanese maintenance crews demonstrated a highly efficient approach to sustaining one of the most heavily trafficked rail arteries in Japan. The project not only improved track quality and safety but also showcased a refined methodology for minimizing service interruption while maintaining world-class railway reliability. The Caterpillar CAT 320DL excavator in the video is equipped with a specialized sleeper-laying attachment instead of the standard bucket. This attachment features multiple clamps designed to grip several sleepers simultaneously. During operation, the excavator operator carefully positions the machine alongside the track bed. Then, the attachment lowers and places the concrete sleepers in their designated positions with precision. The clamps open and release the sleepers onto the prepared foundation one by one or in small groups. After placing a set, the excavator moves forward and repeats the process. The use of this specialized setup enables the machine to handle and lay sleepers quickly and efficiently. This method significantly enhances productivity in railway construction and maintenance by reducing manual labor and speeding up installation. The combination of the CAT 320D's mobility and the purpose-built attachment ensures consistent alignment and spacing of the sleepers throughout the laying process. A highly specialized railway maintenance train, most likely the Placer and Thierer RU 800S. This impressive machine is designed for the complete renewal of track infrastructure in a single continuous operation. With an overall length of up to 177 meters, it functions as a mobile factory on rails. When fully loaded with ballast and sleepers, the unit can reach a massive operating weight of approximately 650 tons. The train efficiently removes old rails and worn ballast, while simultaneously installing new materials with high precision. Integrated conveyors, cranes, and tamping equipment allow every stage of the process to be performed without the need for additional vehicles. Thanks to its advanced automation and coordinated working modules, long sections of track can be rebuilt in a short time. Systems like the RU 800S reduce labor requirements, minimize track closures, and improve safety for maintenance crews today. On the 22nd of March 2017, A specialist team from Hay Rail arrived to carry out the stressing of the first 1,000 meters of continuously welded rail on the Gloucestershire-Warwickshire Steam Railway extension to Broadway. This operation is essential to ensure the track can safely withstand temperature changes and long-term loading. 2 anchor points are established, each consisting of 5 fully clipped-up rail panels, positioned 500 meters on either side of a central pulling point. The size of the gap to be closed at the center is carefully calculated using several variables, including the total rail length, the rail section size, and the current temperature of the steel. To allow controlled movement during stressing, the rail is placed on small rollers at intervals of every 8 sleepers. Hydraulic rams are then used to pull the rails together with precise force, gradually closing the calculated gap. Once the correct stress level is achieved, the rail ends are welded together to form a continuous length. Finally, the entire section of track is fully clipped up, locking the rail securely in place and completing the reinforcement process. The replacement of concrete sleepers on an active railway line begins with careful preparation and protection of the work zone. Before any mechanical operation starts, safety measures are organized to ensure that the track section is fully secured. Workers place protective barriers and warning signals along the line to prevent any accidental engagement with passing trains or nearby equipment. These protection systems create a safe corridor where the maintenance crew and machines can operate without risk. Once the area is secured, the specialized maintenance train slowly moves into position. This train is equipped with mechanical arms, lifting devices, and storage compartments designed specifically for sleeper replacement. The first task is to inspect the existing track condition and identify the sleepers that are damaged, worn, or no longer properly supporting the rails. After the inspection, the crew prepares the section for removal by loosening the rail fastenings and slightly lifting the rails away from the old sleepers. The machine then begins the systematic process of extraction. One by one, the old concrete sleepers are pulled out from beneath the rails. The lifting mechanism grips each sleeper firmly and slides it sideways out of the ballast bed. As each sleeper is removed, it is transferred to a storage area on the maintenance train. This organized collection ensures that the discarded materials do not obstruct the track and can later be transported away for recycling or disposal. With the old sleeper removed, the next phase is immediate replacement. A new concrete sleeper is taken from the onboard magazine of the train and positioned precisely in the empty space. The machine carefully aligns it so that it sits correctly beneath both rails. Accuracy at this stage is essential, because even a small misalignment can affect track geometry and train stability. After positioning, the rails are gently lowered back onto the new sleeper and fastened securely. The process follows a continuous rhythm. Remove a sleeper, replace it with a new one, secure it, and then advance to the next position. The maintenance train progresses slowly along the track, repeating this cycle hundreds of times throughout the work shift. Communication between the machine operator and the ground crew is constant. They monitor the spacing between sleepers, known as the gauge distance, to confirm that it remains within the required technical limits. As the train advances, additional tasks are carried out to improve track quality. Ballast around the new sleepers is adjusted and compacted to provide firm support. Any excess debris is cleared away, and the alignment of the rails is checked visually and mechanically. This ensures that the renewed section of track meets operational standards before regular traffic resumes. Throughout the operation, the protective measures remain in place. Workers remain alert for any unexpected situations, and the entire procedure is coordinated according to railway safety regulations. Music or radio communication can often be heard in the background as the crew works in a steady, practiced routine, showing their familiarity with the equipment and the method. By the end of the shift, a long stretch of track has been renewed with strong, modern concrete sleepers. The maintenance train reaches its final position, and the crew reviews the completed section. Tools are stored, unused sleepers are returned to the magazine, and the old materials are prepared for transport. After a final inspection confirms that everything is secure and correctly spaced, the protective barriers are removed. The track is then ready to be returned to service. Thanks to this organized and efficient replacement process, the railway gains improved stability, longer service life, and safer operating conditions for future trains. A specialized train designed for railway construction and maintenance. This equipment functions as an advanced rail laying and recovery machine, built to replace old rails or install new ones quickly and efficiently. The train consists of several wagons that transport long sections of steel rails to the work site. Integrated cranes and lifting mechanisms automatically unload, position, and lower each rail into its precise location along the track bed. Hydraulic arms guide the heavy components with stability and accuracy, reducing the need for manual handling. By combining transport and installation into one continuous operation, the machine improves productivity and safety. Tasks that once required large crews and many hours can now be completed in a short time with minimal disruption. Such technology increases precision, ensures consistent alignment, and supports the daily demands of modern railway infrastructure maintenance. During the winter period, the unloading of a rail-carrying train requires careful preparation and the use of a special device known as the Stell's coupling instrument. The process begins with clearing snow from beneath the mechanism so that the SLS unit can be charged and positioned correctly. Workers thread a strong steel cable through the equipment and gradually pull the rope along the length of the consist. The cable is guided forward and secured to the ends of the long welded rail strings inside the wagons. Once everything is connected, the crew demonstrates the device and explains its operation. The lower section of the instrument is designed to scrape away compacted snow and loose ballast, creating a path for the rails. Because the apparatus is heavy, several workers are needed to turn and align it in the proper direction. After the setup is complete, the tails of the rail strings are pulled out and placed onto the device platform near the automatic coupler. Cables are then hooked firmly to the rail ends, and tension is applied.
Только точно не знаю. Хвосты плетей вытаскиваются, укладываются на прибор, специальные желоба. Стой. Вперед самый малый 3 вагона.
With the ropes tightened, the locomotive slowly pulls forward, extracting the rails from the cars. Only minimal movement of 3 wagons at a time is enough to begin the discharge. The train advances carefully for about 90 meters, pauses, and then continues in small stages. Fasteners holding the rails are removed, and the unloading operation proceeds under constant tension.
Остановочка 91-я, постоим. Отправляются в желоба.
As the rails slide from the wagons, they are guided onto the prepared ground. The device clears remaining snow and spreads the gravel bed so that each rail string can lie within the required gauge. Workers control the speed to avoid sudden acceleration. Step by step, the consist is emptied, demonstrating an winter delivery method. The 2TE diesel locomotive operates with a heavy maintenance freight train on the Bryukovetskaya to Timashevskaya railway section in Krasnodar Krai. This powerful locomotive is designed for demanding transport tasks and is capable of hauling large loads across long distances. The train moves steadily along the North Caucasus Railway, carrying essential equipment and materials required for railway service operations. The journey, recorded on June 21, 2012, demonstrates the reliability and strength of this classic freight locomotive. Such trains play an important role in supporting infrastructure, delivering supplies, and ensuring continuous operation of regional rail networks. Daily railway activity remains vital. The video shows the complete working procedure of welding railway tracks using the thermite welding method. The process begins with careful preparation of the rail sections that need to be joined together. Workers first inspect the 2 rail ends and clean them thoroughly to remove rust, dirt, grease, and any surface contamination. This cleaning step ensures that the welding area is free from impurities that could weaken the final joint. After cleaning, the rail segments are precisely aligned so that both ends remain perfectly straight and level. Strong clamps and positioning tools are installed to hold the rails firmly in place during the entire operation. Once alignment is completed, a special heat-resistant mold is placed around the gap between the 2 rail ends. This mold forms a cavity that will later be filled with molten metal. The mold is carefully sealed with refractory materials to prevent leakage during pouring. At the same time, a crucible containing the thermite mixture is prepared. The mixture consists mainly of aluminum powder and iron oxide. This chemical combination is essential because it produces an intense exothermic reaction capable of generating extremely high temperatures. The crucible is mounted directly above the mold and secured in position. When everything is ready, the thermite mixture is ignited using a special ignition source. Immediately after ignition, a powerful chemical reaction takes place inside the crucible. This reaction creates temperatures high enough to melt steel rapidly. The molten metal produced from the reaction begins to flow downward through an opening at the bottom of the crucible and enters the mold cavity surrounding the rail joint. As the liquid metal fills the mold, it fuses with the ends of both rails, creating a continuous connection between them. The excess byproduct of the reaction, known as slag, remains separated from the molten steel and stays inside the crucible. After the pouring stage is completed, the molten metal is allowed to cool and solidify naturally. This cooling period is important because it allows the new weld to form a strong and durable metallurgical bond. When the joint is completely solidified, workers carefully remove the mold and other supporting equipment from the rail. At this stage, the welded area is strong, but still rough and uneven. To achieve a smooth running surface, a rail grinding machine is installed directly over the weld. The grinder removes excess metal and reshapes the joint so that it matches the original rail profile. This finishing operation ensures that the welded section becomes flat, uniform, and perfectly aligned with the rest of the track. The final grinding stage is essential for eliminating bumps or irregularities that could cause vibration, noise, or damage when trains pass over the joint. After inspection, the welded rails form a seamless and continuous track section ready for service. Through this carefully controlled sequence of preparation, reaction, pouring, cooling, and grinding, thermite welding provides a reliable and effective method for connecting railway rails in the field. At Port Derence, Turkey, the operation of transporting newly manufactured passenger train coaches to the seaport begins with careful preparation at the rail terminal. Each coach, built by the Turkish manufacturer TUVASAS, measures 26.40 meters in length, 2.90 meters in width, and 4.30 meters in height, with an individual weight of approximately 51 tons. The process starts as the completed coaches stand on the railway tracks near the loading zone, awaiting transfer to maritime shipment. A heavy-duty mobile crane is positioned alongside the track, and lifting slings and rigging equipment are attached securely to the reinforced lifting points on the coach body. After final safety inspections are completed, the crane slowly raises the massive coach into the air and carefully moves it sideways away from the rails. With precise coordination, the operator lowers the suspended unit onto a low-bed semi-trailer connected to a powerful tractor truck. Once the coach is resting on the trailer, workers secure it firmly using heavy chains, steel tensioners, and protective support blocks to ensure stability during road transport. The loaded truck then leaves the rail facility and travels slowly through the port access roads toward the main quay area. Escort vehicles accompany the convoy to maintain safe movement and to control surrounding traffic along the route. Upon reaching the dockside, the tractor-trailer stops beside the ocean-going cargo vessel assigned for the international delivery. A large port crane, fitted with specialized spreader beams, is prepared to handle the next lifting stage. Dock personnel attach the crane hooks to the coach, and the machine lifts the unit steadily from the trailer deck. The crane swings the coach carefully over the open cargo hold of the ship while ground spotters provide continuous guidance by radio communication. The coach is gradually lowered into the prepared storage position inside the vessel. After touchdown, technicians remove the lifting gear and secure the unit with maritime lashings and strong retaining brackets. Identical procedures are repeated for every remaining coach until the entire shipment is arranged neatly and safely within the ship hold, ready for sea transport. A worker uses an angle grinder to perform localized grinding on a section of the railway track. Wearing full protective gear, goggles, and ear protection, he begins by positioning the grinder wheel onto the side of the railhead. The grinding process produces a visible stream of sparks as the abrasive disc removes metal from the surface. Carefully and methodically, the worker moves the tool back and forth along the worn or damaged area, smoothing out irregularities and restoring the rail profile. The operation focuses particularly on the upper corner and side of the railhead, where contact stress from train wheels is highest. The grinder is handled with firm, controlled motion to ensure even removal of material without creating flat spots or dips. During the process, the worker pauses occasionally to inspect the surface and adjust the angle of contact. This type of manual rail grinding helps to maintain rail integrity, reduce the risk of cracks, and extend the life of the track by preventing further wear and fatigue.